What's up everyone? I picked up this Archon Type B Gen 2 recently. It's designed in a way that minimizes bore axis height. This should minimize muzzle flip. I want to find out by how much. I'll be comparing it to a Glock 45, which I think is a pistol design generally regarded as having a low bore axis. This one is lower. And a SIG P320, which is typically regarded as having a higher bore axis. In theory, based on simple physics, bore axis height should matter when considering muzzle flip. However, there are so many other factors that can contribute to muzzle flip or lack thereof. So I want to present some of the basic physics, contributing factors, some measurements and calculations, and then test and compare muzzle flip between these three pistols. Timestamps will be provided as always. Skip around as you please. This is going to be a lot of fun. Let's get into it. I'm going to define recoil as any movement of the pistol associated with a round being fired or the action cycling or reciprocating. I like to break down pistol recoil behavior into three components. First is the straight back shove that is an equal and opposite reaction to the energy of the bullet and gas leaving the barrel. One could make a simplifying assumption that this rearward force acts along a line coincident with the bore axis or a line drawn through the center of the barrel bore. Second is muzzle flip. This is the moment or torque that is a result of that rearward force along an axis that has some perpendicular separation distance from a pivot point of the pistol in our hand. Third is muzzle dip. This is a result of the slide coming back forward into battery. This is more of a function of slide mass, recoil spring weight, friction, the force needed to strip around out of the magazine, and the barrel locking action. Let's look at a simple cantilever beam that is fixed to the wall on one end and a force applied to the other end. This is a statics problem where the sum of the forces equals 0 and there's no acceleration, so it's probably not the best analogy for our dynamic system. However, this is one of the simpler ways to consider shear force and torque. Hopefully I can explain it and connect it to recoil forces in a way that makes sense to you. When this force is applied, there are two reactions back here at the wall. There is shear, which is the reaction to this straight down force. What if the point load is applied right there against the wall? This blue arrow would be the reaction force opposing it. If this force was great enough, it would shear this beam off. What if this beam was made of a bunch of little layers laminated together in this orientation? The force applied here would want to shear this layer, and then this layer, this layer, this layer, this layer, all the way back to the wall. That is where this shear reaction force comes from. It will always be here where the beam is attached, regardless of how far away this force is from the wall. Then there is the reaction moment. This is a pure torque about the fixed end of the beam due to this applied force having some perpendicular separation distance from it. The magnitude of this reaction torque will be proportional to this separation distance and the magnitude of the force applied. The further this force is away from the wall, the higher this torque will be. That's because torque is force times distance. Now, let's just rotate this. We will call this fixed end the pivot point of the pistol in our hand and the line that the force is acting along the bore axis. The shear force is the straight back shove you feel. And in our dynamic situation, your hand provides the reaction force, but it's not rigid, so some linear movement occurs in this direction. The reaction torque is provided by your hand trying to keep the pistol flat. That's also not rigid, so some rotational movement occurs and we get muzzle flip. We will be focusing on muzzle flip in this video. That is the aspect of the recoil motion that is most associated with bore axis height. The further that separation distance, the more mechanical advantage that force will have, creating a higher torque about the pivot point, which results in more muzzle flip. For the remainder of this video, we will consider this pivot point to be our wrist. There are a lot more characteristics of a pistol and the person shooting it that can possibly affect muzzle flip just besides the bore axis. That's where we start to deviate from a simplified model and get into real-world situations that get much more complicated and less predictable. When considering these factors, I'm only speaking of their effect on the pistol from the moment the slide starts traveling rearward when the shot is fired to when the slide hits the frame abutment at the rear of its travel. When the slide starts coming back forward, that's kind of where muzzle flip ends. The following factors are the ones I could come up with. Let me know if I missed any. The overall mass of the pistol, the mass of the reciprocating components, slide acceleration and deceleration, the velocity of the slide when it hits the rear of its travel. The faster it's moving, the harder it hits the frame, the more it will pitch the pistol back. Recoil spring force. This affects both the velocity and acceleration of the slide and is closely coupled with the mass of the slide to dissipate the energy from the round being fired. The mass of all the non-reciprocating components. The barrel unlocking action. How far it has to move and at what angle. Is it an abrupt change in motion like in a Glock, or is it a smooth arc like in a 1911? Does the barrel tilt at all during unlocking? Barrel length and profile. The grip length. How much grip do you have to hold on to? Is your pinky finger hanging off the bottom and not able to contribute to the force applied to resist muzzle flip? Grip texture, grip angle, grip size and shape, and generally how it fits in the shooter's hand, and the shooter body mechanics. How strong are they? How big are they? How experienced are they? How do they hold the pistol? Let's look at the pistols I chose for this comparison and why. Ideally, we would have 3 identical pistols with only varying bore axis height to isolate the effects of that variable. That's not really feasible. I chose these first and foremost because they are pistols that I own and can use for testing, but I think they'll make a pretty good comparison. They have varying bore axis height. Unfortunately, the Archon does have a different barrel locking mechanism. It's not a tilting barrel like the other two. That is a result of its low bore axis, or rather the low bore axis could be achieved because of the locking mechanism. They're all chambered in 9mm. They all have polymer full-size grips, about a 4-inch barrel. The Archon has the longest barrel at 4.3 inches. They have very similar recoil spring weight, all 17 to 18 pounds. There is some variation in mass between the pistols. I will be quantifying those differences later in the video. I will shoot them with no optic covers in place, no lights or weight added to the grip or frame. The Glock has better grip texture than these two, but I think the P320 grip size, shape, and angle actually agree with my hand best. You know I like to port my pistols, but surprisingly, none of these pistols are ported. I want to measure and quantify some of the aspects of these pistols that I think will affect muzzle flip the most. First and foremost is bore axis, obviously. We need a datum to compare bore axis between the pistols. I will consider this datum the highest point my hand contacts on the back strap with a normal firing grip. I will measure from this datum to the bottom of the slide, and then from the bottom of the slide to the center of the bore at the muzzle end. Next is the mass of all the non-reciprocating components, the grip, internals, barrel, and recoil assembly and magazine. They will all be loaded with the same amount of ammo, so the mass added from the ammo will be constant. The barrel and recoil assembly do kind of reciprocate, but they're generally considered non-reciprocating. Heavy full-length guide rods and heavy profile bull barrels are used to soften recoil and reduce muzzle flip. Finally, the mass of the reciprocating components and how that mass is distributed. This is the slide and everything on it. More reciprocating mass should result in more muzzle flip. I was going to get into a long discussion with diagrams and equations about force, mass, acceleration, torque, moment of inertia, and angular acceleration to explain how reciprocating mass affects recoil, but I don't think that's necessary. The effect the reciprocating mass has on the recoil of a pistol is actually pretty intuitive. The more mass there is flinging around up here, and the further away it is from where we hold the pistol, the more it will move the pistol around and affect recoil. I measured the reciprocating mass of each pistol, but I want to take it a step further. I made a detailed model of each of these stripped slides. I did this so I could have the program calculate the location of the centroid, or the center of mass of the slide, for me. Once resolved into a point mass, I can measure its location. This will help give us an idea about how much of an effect the mass of the slide will have on muzzle flip based on how high its centroid is. The slide on a pistol with a higher bore axis will consequently have a higher center of mass. I only modeled the strip slides. That shit already took me like 3 hours or more per slide. I didn't want to model all the internals. This shouldn't affect the location of the centroid that much. I applied material properties to these models, and they all came out to within 3 grams of the actual mass of the stripped slide as measured on my scale. The center of mass, its location is pretty intuitive to guess. It's really easy on symmetrical shapes. There are tables of tabulated centroids of different shapes, and there are moments of inertia about those centroids. But let's look at this slide. We can consider mass distribution in 3 axes. Along this axis, the mass is going to be pretty symmetrical. This cutout on this side may bias the center of mass in this axis a little bit this way, but it's going to be relatively centered. In this direction, there is more material and mass towards the back. So along this axis, our centroid will probably be biased a little bit this way. And in this direction, there is more mass at the top than the bottom of the slide, so our centroid will also likely be biased up this way just a bit. Let's look at the location of this centroid. It shows up kind of where we expect, right? A little bit further to this end, a bit higher up in this direction, and relatively centered this way. I measured the location of all 3 centroids down to the bottom of the slide, so I could add that measurement to the distance from our datum on the back strap up to the slide. Now I have a vertical location of each centroid measured from the same place as bore axis height. Let's make some predictions about the outcome, then we'll get to the testing. I think most of us would guess that this pistol will have the most muzzle flip. This will have the least. This will be somewhere in between. What's harder to guess, for me at least, is by how much. I just put the measurements we took into a spreadsheet. I have color-coded the values red, yellow, and green. Green is good for muzzle flip, red is bad, yellow is somewhere in between. If the pistol bore axis is higher, it should result in more muzzle flip. The lowest bore axis is green, the highest is red. Higher reciprocating mass centroid, more muzzle flip. More reciprocating mass, more muzzle flip. This last one's backwards. More non-reciprocating mass should reduce muzzle flip. So a higher number here is better, or green. The pistol or column with the most red should have the most muzzle flip. The pistol with the most green, the least muzzle flip. Then yellow is the guy in the middle. The reciprocating mass is very close on all the pistols. The Archon has a lot going for it in terms of minimizing muzzle flip. Lowest bore axis, lowest reciprocating mass height, and much more non-reciprocating mass. Can we use this data to accurately predict how much more muzzle flip the other pistols will have than the Archon? Not likely. I think there are too many other variables that are not captured here that will affect muzzle flips. Let's quickly go over what variables I'm attempting to control. The pistols I chose and how I set them up, which I explained earlier. So the differences we see in muzzle flip will be affected as little as possible by other factors than the bore axis height, slide mass, and the location of the slide mass centroid and the non-reciprocating mass. The differences in barrel locking action between these two and this one may be a contributing factor. Can't do anything about that. I'll shoot the same ammo for every test. Blazer brass 115 grain. In my experience, over thousands and thousands of rounds. It's pretty consistent, but of course I cannot control the consistency of that ammo from the factory. Environmental conditions. Obviously I can't control these, but I can shoot the pistols on the same day, in the same location, close to the same time, so ambient temp, humidity, etc. will be pretty close for each test. My grip on the pistol. I like to think after 25 odd years of shooting, I know how to build a consistent grip on a pistol, but I am unfortunately human, so there will be small variation. There will also be variation due to the differences in grip, size, shape, texture, and angle. I can control how I collect data and analyze data and how I report it. We'll get into that in a moment. Pretty much everything else I can't control. For each test, I load 7 rounds into the magazine. I only record data from the middle 5 shots. The first shot allows me to settle into my grip, and the last, the slide locks to the rear, which changes the recoil impulse. I film this at 240 frames per second. For each of the measured shots, I take a still right before the shot, then one of maximum muzzle flip angle. I overlay the 2 images, then put them into image analyzing software to measure the angle of muzzle flip using the top of the slide as a datum. I would consider the measurement uncertainty of this method to be maybe plus or minus half a degree. For each data set, I calculated the mean and standard deviation. You can see that as the muzzle flip increases, so does the variability in the data shown by the larger standard deviation. I think this is due to a more violent recoil impulse exposing more inconsistency in my grip. To help visualize the data, I created this plot. The top of each bar represents the mean muzzle flip angle for a pistol, then the error bars represent one standard deviation above and below that. I think the inclusion of the error bars gives us a range of muzzle flip angle values that may account for variability like slight differences in ammunition or my grip from shot to shot and the uncertainty of my measurement method. This angle range may get wider or narrower or shift up or down depending on who is shooting the pistol. The Archon muzzle flip angle was between 12.7 and 12.9 degrees with a mean value of 12.8. The Glock muzzle flip angle was between 13 and 13.7 degrees with a mean value of 13.4. The SIG muzzle flip angle was between 15.7 and 17 degrees with a mean value of 16.3. I struggled with how to compare this data and how to report that comparison. I'm going to explain why I chose to compare the data the way I did. I won't get into a discussion about ethical data collection analysis and manipulation, but this is squarely in that territory. I put a great deal of effort and thought into accurately and fairly reporting my data. With this data, I could report it as a percent increase. For example, the SIG has X percent more muzzle flip than the Archon, or a percent decrease. The Archon has X percent less muzzle flip than the SIG, or as an absolute percentage difference between the muzzle flip values. The absolute difference in muzzle flip between the SIG and the Archon is X percent. I think this is the best way to report the data for this comparison because I'm not comparing the muzzle flip of a pistol to the muzzle flip of that same pistol after I change its bore axis. These are different pistols. I want to show how those different comparison methods give different answers with the same data and why it's important to select an appropriate method. Say I measure an average muzzle flip angle of 15 degrees on pistol X and 20 degrees on pistol Y. The percentage decrease in muzzle flip from pistol Y to pistol X is 20 minus 15 divided by 20. You use the larger of the two values in the denominator because it is decreasing from that larger value. This gives us a 25% reduction in muzzle flip. Pistol X has 25% less muzzle flip than pistol Y. This is how I compare and present reduction in muzzle flip in my barrel porting videos because it's the most accurate way. The percentage increase in muzzle flip from pistol X to pistol Y is 20 minus 15 divided by 15, using the smaller of the two values in the denominator because it is increasing from that smaller value. This gives us a 33% increase in muzzle flip. Pistol Y has 33% more muzzle flip than pistol X. Both these equations are correct and valid ways to compare the raw numbers in terms of a percentage change, but they give quite different values. I don't think it's appropriate to use either to compare two separate pistols. These are for comparing two different states of a single entity, not two separate entities. So the way I will be comparing these is an absolute percentage difference. The absolute difference in muzzle flip would be 20 minus 15 divided by the average of the two values. I could say the absolute difference in muzzle flip between pistol X and pistol Y is 28.5%. I will give a range based on one standard deviation above and below the mean value than the absolute difference between the mean values. The absolute difference in muzzle flip between the Archon and the Glock is 0.8 to 7.5%, with a mean absolute difference of 4.6%. The absolute difference in muzzle flip between the Archon and the SIG is 19.6 to 29.0%, with a mean absolute difference of 24.7%. The absolute difference in muzzle flip between the Glock and the SIG is 13.6 to 26.7%, with a mean absolute difference of 19.5%. You can see since the testing I got my Glock back in its standard trim. There is a large portion of recoil feel that is subjective based on the shooter. That's why I do the experiments, collect and analyze the data, so you're not just listening to me talk about how these pistols feel to shoot, because they probably won't feel the same to you, but I will quickly give you my thoughts as we wrap this up. I shot the Archon, then immediately picked up and shot the Glock. I shot the Archon, then immediately picked up and shot the SIG. I shot the Glock, then immediately shot the SIG. I didn't feel much of a difference between the Archon and the Glock. I noticed a significant difference in the recoil behavior between the SIG, P320, and the two other pistols. I hope this was interesting, informative, entertaining, or helpful to you in some way. Were you surprised by the results? The results were in line with my predictions. However, I expected there to be more of a difference in muzzle flip between the Archon and the Glock. They felt really quite similar to shoot, and I think the data reflects that as well. Can we attribute the difference in muzzle flip between these pistols solely on bore axis height? Absolutely not. I hope I've given you an idea of all the factors that may contribute to muzzle flip and why testing like this is so difficult. As always, thanks so much for watching. Stay curious. I'll catch you next time.